Yeah. Just remember that the meeting will be live streaming also on YouTube, so you can find the link in the chat. We will put in a minute, and also in the Laura Bassi Series webpage. But before to start the seminar, today's seminar, and to give time to our colleagues to join us, I will give way a short video about the life of Laura Bassi. Federico, please, if you can.
Laura was born on 29 of October 1711. In 1732, she earned the degree of Doctor in Philosophy from the University of Bologna. A few months later, because of her remarkable scientific skills, the Senate of the University assigned her a position at the chair of Philosophia Universa, that is, of natural philosophy. In the following years, the young woman continued to study. In 1738, she married Giuseppe Verratti, a doctor in medicine who shared with his wife a keen interest in the study of nature. In 1745, Pope Benedict XIII admitted Laura Bassi among the elite group of scholars named Benedictine academics, but only as a supernumerary and not without resistance. Filling this role, she had to present at least one original dissertation a year. In this way, Laura played an active role inside the Bolognese scientific community. For performing her talks, Laura carried out several experiments with her husband in her own home, in a special laboratory that the couple had equipped with the most advanced tools and machines of the time. This laboratory was used not only for her personal research, but also for the private lessons in experimental physics that Laura Bassi held for philosophy and medical students of the university. The almost 30 years of high-level lessons held by Laura at her home earned her the assignment of the position, this time effective, of Professor of Experimental Physics in the Institute of Sciences in 1776. Only 2 years later, on the morning of February 20, 1778, Laura Bassi died suddenly after having participated in a session of the Academy of Sciences the previous evening. This woman, a forerunner of female emancipation, remains an admirable example for all women of science still today.
So I think it's time, more or less, to start up. So it is my pleasure to introduce today's speaker, Claudia Gutierrez. She is a Finca fellow in the Department of Physics and Astronomy at the University of Turku in Finland. And her main research interest is core-collapse supernovae, the progenitor, and the host galaxies. She obtained her PhD in astronomy in the University of Chile, in Chile in 2016, in the supernova field. And she and Claudia have also worked at the European Southern Observatory in Santiago as part of the ESO's studentship program, and as postdoc researcher in the University of Southampton. So without any further delay, I pass the baton to Claudia, who will help us today to better understand hydrogen supernova. Thank you, Claudia.
Thank you, Nancy. Can you see my slides?
Yes, yes.
Okay. Thank you very much for the invitation. I'm very happy to be here to share with you my research. As Nancy mentioned, I work in the supernova field. and mainly in hydrogen-rich supernovae. So today I will show you the studies that we are doing in this field and how we are analyzing the observational diversity of these objects. Okay, so to start, just like a motivation or the reason why we study these objects, supernovae are one of the most energetic events in the universe. They are very luminous, very bright objects that we can see very far. And that's the reason why they are powerful distance indicators. Actually, in 2011, the Nobel Prize was for 3 astronomers who work with supernovae, studying the expansion of the universe. So these objects are very bright that in the peak, their luminosities can be comparable to the total light of their host galaxies. So here in the slide, I have 2 examples. On the top, we have a supernova 97A, that is the best supernova study until now, exploding the Magellanic Cloud, very nearby. It was visible from the south, and on the left, we can see the field where the progenitor was located. You can see with the arrow where the progenitor was. And on the right, we see a very bright spot that is the supernova. Here in the bottom, we have supernova 2013 CU, and it's the same. In the left panel, we have the galaxy, so it's a spiral galaxy. And on the right, we can see clearly where the supernova was located. So as these objects are very bright, we can see them very distant, and they are used as distance indicators. But this is not the only role supernova play in astronomy. They are also very good in the stellar evolution, in the chemical enrichment of the ISM, and triggering star formation. So as I said, these are very energetic events, and supernovae are the final explosion of some stars. Not all stars end their lives as a supernovae, just some of them. And for this talk, I will focus the analysis in the hydrogen-rich supernovae, or the so-called II Supernovae. These objects are produced by the final explosion of massive stars. So when we are talking about massive stars, these stars are more massive than 8 solar masses. And in this case, these stars, before the explosion, they retain a significant amount of hydrogen envelope, and that's why we see the hydrogen in the spectrum. So here in the bottom, we can see a spectrum of a II supernovae. This is a couple of months after the explosion, and we see the hydrogen lines. And when the temperature decreases, another lines start to appear, like iron, sodium, and calcium. So normally in the supernova field, we do the classifications or subclassifications based on the absence or presence of several lines in the spectra. So if we see the lines like the hydrogen, we call II, but if we don't see the lines, we call I1. But in the case of II supernovae, the subclassification was based on the light curve shape, the morphology of the light curve. So in the 70s, 80s, people were observing these objects, and they realized that they were 2 distinct types or subtypes of II supernovae. That ones that they were showing a quasi-constant luminosity for a few months, or a plateau that we call II-P from plateau, and other subtypes that they were showing a linear decline for several months, and we call II-L. People believe at the beginning that the progenitor of these objects were different. However, with more data, with more analysis, we actually found that there is a large diversity in the light curve morphology. So in 2014, Anderson et al. Published more than 120 supernovae, the light curves in the V band, and this is the diversity we see. So we see that these objects have a large range in luminosities. They also have different lengths in the plateau, different decline rates. That can tell you something about the progenitor stars. But in the same year, we also analyzed the spectra, and in that moment, we just focus our analysis in the H-alpha P Cygni profile, that is the most characteristic line of II supernovae. So as I say, the II-L and II-P, the only difference was based on the light curve, But then when we explore, and the spectra in principle was similar, but when we explored the H-alpha P Cygni profile, we saw that there is also a large diversity in these lines. So some objects, they don't show their absorption, or they have a flat absorption, like this one here. They have different kind of profile. Ones were like very narrow, other very broad. So different configurations that suggest that there is also like a large diversity there. So when we compare the measurements from the H-alpha P Cygni profile and the Likers, we see that there is a correlations continuous in this supernovae. So before the idea in the 80s was the II Supernovae. The models predict that the progenitors were red supergiants, and in 2003, 2005, that turns out to identify the first progenitor of a II Supernovae. And this technique is called the direct identification of the progenitor. So the idea is that if we have II Supernovae very nearby, and we have pre-explosion images, so archive images, we can go and look up for the progenitor star and have my progenitor candidate. So here in these three panels, I will show you how the technique works. So in the middle, in the panel B, we have the supernovae. This is a II Supernovae, 2008 BK, around maximum light. So the idea was that as this object was very nearby, people went to archive images. This is from FORCE to in BLT, and they were locating the position of the supernovae. And this star here in red is the supernova candidate, the progenitor candidate. So to confirm if this red star is the candidate, we need to wait around 2-3 years when the supernova disappears to observe again the same field and see if the object is still there or disappeared. So in this case, in 2010, the observations, they observed the same field. This is multi-band image. And as we can see, the object disappeared. So that was a confirmation that this red star was the progenitor of 2008 BK. So using this technique is very powerful to identify progenitors. However, there are many limitations that we can only do it with very nearby objects. And in addition to that, we need pre-explosion images in multiband. So far, there are around 25 progenitors identified. Most of them are red supergiants, which is consistent with the predictions of theoretical models. And in 2015, Stephen Smart did a compilation of these objects and analyzed the initial mass of the progenitors. So here we have around 15 supernovae, and in the x-axis we have the initial mass. So with these multi-band images and using stellar models, evolution models, we can constrain the progenitor mass of these objects. And as is shown here, so they constrain the mass, but the problem was that they only find masses between 8 and 18 solar masses. Why this is a problem? This is a problem because based on the observations in the Milky Way, we know that red supergiants can be massive up to 25-30 solar masses. So there is a range of higher mass that is missing. So when we use the salpeter IMF, we can see that these massive progenitors are not there. So this is a problem that we now call the red supergiant problem. Some people claim that maybe there are problems when we measure the luminosities in these images, or there is a problem also that we don't know how to deal with extinction. So that's why we don't see these more massive progenitors, but people are now working on that, trying to figure out what is happening. So this is one way to constrain the progenitors of these II supernovae, but it's very limited, very few objects with that. So there are other ways that we can do statistical analysis of these observations, but we can also compare observations with models. For that, we can use either the Likers or the spectra, or both. The problem is if we use both, it's too much time consuming there. But if we are using the analysis using the spectra, we can do it in the photospheric phase. And the photospheric phase is the early phases where the hydrogen envelope is optically thick. So we just see the outer pass of the ejecta of this material that is expanding. And the characteristics of this photospheric phase is we see these P-Cygni lines or sun absorption lines, while with time, when supernovae is older than 150 to 100 days, we see that this envelope is transparent and we can see the core very nearby the core. And we can have an idea of the abundance of the star, how was the explosion, it was asymmetric, or this kind of things. So we can do the modeling even at the beginning or late to have different approaches about the supernova progenitor. So if we do statistical studies, we basically measure the parameters from the light curve, as I showed before, different magnitudes, the magnitude at peak, at the end of the plateau, different the length of the plateau, how fast the object is declining, and we can compare these parameters with parameters from the spectrum. For example, the expansion velocities that we measure from the minimum of the absorption lines, or the intensity of the lines, the ratio of the absorption to emission of H alpha. And using that, we find correlations. Some correlations are shown here. For example, we compare the velocity, the expansion velocity of different lines with the absolute magnitude at peak. And we found that in general, brighter supernovae expanded faster. So, and that turns out it can be more energetic. So these correlations also show a continuum, and this observed continuum, both in the light curves and the spectra, suggests that II supernovae are coming from the same progenitor population. So this is a way that we can have an idea of the progenitors of supernovae. But if we go now for modeling, so we can model, for example, the light curves using hydrodynamical models, and with the light curves plus the expansion velocities, that is measurements are from the spectra, we can infer the progenitors and explosion properties. So here there is a set of different supernovae. On the left, there is the light curve. On the right, we have the expansion velocities. And we see some good fits. That fits comes from different configurations that the people use to constrain progenitors. So this work was accepted at the end of last year, so I think it's published now in January, from Laureano Martinez. But one interesting thing from this work is that even using these hydrodynamical models, we still see the red supergiant problem. So using a gold sample, that is objects that had a very nice light curve coverage and also good expansion velocities, they estimate the initial mass, so same as the plot that I showed before. And we see here that most of the objects have masses between 8 and 18 solar masses. There is just one object that has a mass about 20 solar masses, but like 60% of them or more, they have masses below 12 solar masses. So this is very important, and this is another way to see how the progenitors are, and we still have the problem finding high mass progenitors. So in the paper, there are also some claims that maybe we have problems doing the modeling and we are doing something wrong, and that's why we don't find these more massive progenitors, or there is in fact a problem with the IMF that we are considering here. The other way to constrain the properties is using the spectral modeling. As I said, at early phases, when you see the P-Cygni lines or these absorption lines, you can have an idea of the metallicity, radius, and kinetic energy. While at late times, when you see these emission lines, we can have an idea of the progenitor mass. This is based on the stellar models, but also supernova models, that shows that the helium core correlates with the progenitor mass of the star. So if we go to this point at late phases, and here in this plot I'm showing you a nebular spectrum, these are two models, 12 and 25 solar masses, we see that in general, there are not much differences in the lines between the two models, but for the oxygen 1, 16, 00 and 6064, we see there is a huge difference. So this line, the oxygen 1, is a good proxy, is a tracer of the mass of the progenitor star. And for example, in 12 solar masses, we see that the strength of the oxygen line is weaker compared with the model at 25 solar masses. So this technique, the comparison of the observations with model, also help us to have an idea of the progenitor mass. And again, we have a lack of higher mass progenitors. So using 3 different techniques, we see that there is this lack of progenitors. So if we go to early phases, in 2014, Luc Desart developed 4 different models for a 15 solar mass progenitor with different metallicities, 0.1, 0.4, 1, and 2 times solar. So in these 2 plots, I'm showing you the spectral sequence of a model of 0.4 and 2 times solar. And we see that they are evidence differences. For example, in 0.4, the region between H alpha and H beta, these 2 PCD lines, is very empty. So there are no lines in there in the middle. Only at 70 days, some lines start to appear. While if we go to higher metallicity, between H alpha and H beta, this region is populated very fast for many metal lines. So this could suggest that metallicity has some influence in the evolution of type II supernovae. So here on the left, we see again the models, but in this case, these models are around 50 days to show how different are the spectra. So we go from bottom to the top, from 0.1, 0.4, 1, and 2 times solar, and we see that there is very few lines and there are many lines when it's higher metallicity. But if we focus just in the iron line 5018, that is between these 2 Dutch vertical lines, we see that at 0.1 solar metallicity, the line is very weak, but as metallicity increases, the strength of the line increases. So we wanted to test these models, and for that we need basically 2 types or 2 different observations. One that is coming from the supernovae, and we need the spectra at a particular epoch. We select again 50 days from explosion, but we also need the measurements of the metallicity, and the measurements of metallicity, they are coming from the H2 region nearby to the supernova location. So for supernova 2003 BL, so we have the spectra here around 50 days. In blue, we highlight the iron line, the 5018, and it's strong. And when we see the H2 region, so here are marked the lines that we normally use to estimate the metallicity or the oxygen abundance, we see that for this object that has this strong iron line, the region has a high oxygen abundance. While for supernova 2007 OC, that the line is weaker, is quite weak, we see the H2 region. We measure the ratios of these lines, and we estimate that they have a low oxygen abundance. So this is going in the same direction of the model predictions. So if that is the case, type II supernovae can be used as metallicity proofs, and that's very good because the lines in the supernova are broad, so they are easy to measure. So to test that, we also compare the oxygen abundance in the y-axis with the equivalent width of the iron 5018 at 50 days from explosion. So these are the measurements here. And we see there is a correlation. On the left, we have 44 objects, and we have a correlation of 0.5. This is using the Pearson correlation test. But when we go to the gold sample, this sample has like a better data, better measurements. So of course we decrease the number of objects, but the correlations increases 0.78. So this is good because maybe we can use this object as metallicity proofs, but we need to explore more things. In particular, because when we see here in both plots, there is a lack of objects at low metallicity. So we have only 2 objects in this region, and that can create some differences in the analysis that we are doing. So if we go and see how are the galaxies of these objects, how bright are the galaxies, we find that for the same sample that I'm talking to now, the hosts are most of them bright. There are very few a low luminosity host. This is in the B band. So we said that a low luminosity host based on the Magellanic Cloud. So we said minus 18.5. That's the limit. And if we see there are like I don't know, 5 objects just in this low luminosity host. And so you see, maybe some of you are confused because I'm changing from metallicity to luminosity, but this is because there is a correlation, the metallicity luminosity corrections that shows, this is from Tremonti 2004, but there are many works showing these correlations. Also, for example, the Khalifa that has many more observations. And it's basically that if we have a very luminous galaxy, a bright galaxy, overall the metallicity is higher compared with a faint galaxy. So because of that, because we have this lack of objects in low luminosity host or low metallicity environments, we can expect differences, and this is based on the theoretical models that said that in massive stars, the mass loss is driven by metallicity. So maybe we are losing something here. So to see what is happening there, we need to fill this gap to find objects at low metallicity environments. So in 2014, we started the follow-up of II Supernovae in low metallicity or low luminosity host galaxies. For now, we have more than 70 II Supernovae in these environments. This project is part of the IPESTO collaboration. It's an European and includes also Chile collaboration. Most of the data, the spectra are coming from La Silla in Chile, and most of the light curves are coming from Las Cumbres in collaboration with the group, the Supernova group there, but also with the time that the PESTO collaboration applied for. We also have some data from NATS, the NATS collaboration, the observations in La Palma, from Liverpool telescope, and for the host galaxies, we need big telescopes because the galaxies are very faint, so we have data from FORCE and MUSE. In 2018, we did a first analysis of this sample. At the moment, we have around 30 supernovae. And here in this histogram on the right, I'm showing you just how the work we were doing. So again, the Anderson 16, that is the sample that I'm showing on these slides. The mean value was minus 20.3 or less. There is also a sample that is Tadia 2016 that was minus 19.2, but with the sample that we started to collect, we went down to minus 16.4. This is the luminosity in the R band for the host galaxy. Now, as we have more data, so on the right, this is just a preliminary plot that we are going down in brightness even more. So the mean now is minus 16. And if we see here, instead our sample is 46, is less than 70, and it's because some of the host galaxies are very faint that we don't have observations yet. So that means that they are very, very faint, so this value is going down a bit more. In 2018, we compared different things to see if we find differences in II supernovae at high and low metallicity. And we didn't find a lot, but for example, here in the left panel, we showed so we split the sample, II2s in low luminosity host. This is II2s in host galaxies fainter than minus 18.5. This is the orange ones, and in high luminosity host, the green ones. So when we compare the velocities, we don't see differences. And we didn't see difference neither with the plateau duration. So if the plateau is longer, that means that the amount of hydrogen is bigger and the recombination stays longer. So longer plateau suggests that a more massive envelope mass. So we didn't find a correlation between the hydrogen envelope mass, so this is the plateau or the optically thick duration phase, neither the explosion energy or the expansion velocities with metallicity. However, we found that there is differences in the strength of the lines. So for here in this plot on the left, we have the equivalent width of 4 different lines: iron, H alpha, sodium, and scandium. And basically, II supernovae in low luminosity host, the orange distributions, display weaker to the equivalent widths of all lines. So when we compare this, that is like the general result, with the models, we are confirming the model's prediction. So in these two plots on the right, we have the equivalent width of the iron line as a function of time, so how the lines evolve as a function of time. And on the left, the II supernovae in the high luminosity host, on the right in low luminosity host, compared with the models that are the brown lines. We can see that at high luminosity host, supernovae are following the branch of solar metallicity, while at low luminosity host, they are following the 0.4 solar metallicity. So that confirms the model predictions. However, so this is the first important result, and we are now trying to obtain more data, in particular for the host galaxy, to see if II supernovae can be used in metallicity proofs. But another thing that we found is that peculiar II supernovae are appearing in this low luminosity host. So if we go again to 87A, that is the most studied supernovae, when was detected, was discovered, the spectrum showed these hydrogen lines and was classified as a II supernovae. People were very excited because finally they can have an idea of the progenitor of these objects. However, when the observations continue and they were observing the light curve, they noticed that the light curve was completely different to the previous objects that we have. It was not flat, so it didn't show a plateau, it didn't show a fast decline, it was showing a long rise to peak. The rise to the peak is about 85 days, so that was not expected. This object is in the Magellanic Cloud, is a low metallicity, so something is happening there. But now that we have more data, the kind of these II supernovae that shows this long rise to the peak, that they are called now 87A-like objects, we find that they preferentially explode in low luminosity host galaxies or low metallicity. There are a few of them that they have the metallicity near solar, but most of them are in these low metallicity environments. And based on the progenitor, on the light curve shape and also in other measurements, the progenitor is a blue supergiant. So these objects are coming from a different progenitor than the standard II supernovae with a plateau or a linear decline. So something maybe is happening in this low luminosity host. And this is not the only objects that have this kind of weird things. In 2017, Giacomo Terreral published a II supernovae, so based on the spectrum as the hydrogen lines, was classified as II, had a long rise to the peak, but if we compare with 87A, this is much luminous and broad than the 87A light curve. So to explain these peculiarities, we use different explosion mechanisms. In this paper, so the supernovae that I was talking till now, they are coming from the standard explosion mechanism, the neutrino-driven, but that has a limit. So for these very exotic objects that have very high luminosities, we cannot explain it with that. And some other scenarios have been proposed, like for instability, magnetar, fallback, but there's still not an agreement in which of these scenarios or mechanisms can satisfy the observations of these objects. There is one very string II supernovae, that is the IPTL 14HNLS. The spectra are consistent with that II. The only problem was that the spectra didn't change for about a year. So basically day after day, the spectra was the same, but the liquor shows a very unusual behavior, done ups and downs many times. And again, we cannot explain that with the neutrino mechanism. So here we have the cobalt decay. We need exotic explosion mechanisms. All these works I put here are trying to fit the observations, but until now, we don't know what is happening with this object. We don't know the kind of progenitor or the explosion it had.
Sorry, Claudia. Sorry,
Yes?
Claudia, you have 10 minutes more.
Yeah, perfect. Thank you. So we have another object, the 2015 BS. This is the first supernova that we started to follow up as a part of the PESTO collaboration. And when we saw the spectrum 50 days, we were very happy. I'm showing here in pink, because the spectra was basically a copy of the templates of the models at low metallicity. The problem we have was that the object went behind the sun. So when we recovered the object, we observed it again in the nebular phase, and the nebular phase was very unusual. So here in blue is the observation, the nebular spectrum of 15 BS, compared with two different models at 15 and 25 solar masses. If we just focus in the line that I said before, that shows significant changes, that is the oxygen line, that is here. I hope you can see my mouse. The oxygen line is between the two models. So the conclusion from this comparison, and also based on the spectral early phases, is that the progenitor mass is between 17 and 25 solar masses. And as you may remember, we had this red supergiant problem, and we are just finding progenitors up to 18 solar masses. So if the progenitor of this object is more massive, maybe we are missing this massive progenitor because we don't have a lot of data in low luminosity hosts. So there is maybe a link between the high mass red supergiant progenitors and low metallicity objects. We also have this, the 16C3CJE. The object, we see the light curve, shows a plateau at the beginning, so nobody was very enthusiastic about it. But when the light curve start to go up, we went for a classification. We realized it has the hydrogen line, so it was classified as II Supernovae. The difference of this object is the lines are very narrow, and that suggests very low expansion velocities. So, and the other different thing in this object, so the plateau going out, up, similar to 87A, and then here we have the tail that was not following the cobalt decay, that is the standard mechanism, was flat. So we need a different or a extra source of energy to explain that. For this object, so we try, we explore the fallback scenario. That means that when there is the collapse, there is some material that is accreting there in the central object, and that powers the light curve, in this case at late phases. So we explore this, including the fallback scenario, for two different stars, one with 15 solar masses, and the configuration was like a red supergiant, so extend a progenitor, and the other one, 40 solar masses, but more compact, like a kind of blue supergiant. You can see that both models and overall reproduce very well the evolution of this object. However, it's better, the fit is better, at least at the beginning, for the red supergiant-like star. So this is an object that we also need a different explosion mechanism. The 17IBV was a fast evolving II Supernovae. We have here a gap in the observations because the object was behind the sun, but when we recovered, continues following very fast. But the important part of this object is the nebular phase. In II, the nebular phase, the most strong line is H alpha. And you can see here that the first three spectrum is consistent with a like standard II nebular phase But after 240 days, the spectra change completely, and H alpha is just decreasing the intensity, while oxygen and the calcium line, the intensities are increasing. That was never seen before, and I don't remember any other object with these characteristics. But in addition to that, after 500 days, there is again a change, and we don't see many lines. We just see a broad H alpha line that suggests some interaction. So based on the nebular analysis and also some attempts that we did to explain the lie curve, that favors a binary progenitor and also an asymmetric explosion. So something is happening there. Last year were published also many other weird or uncommon objects, type 2s, that they were showing, like again, this kind of IPTF 14 generis like light curve. Not many changes in the spectra, but the light curve showing this going on down. And also this 18HM FM that shows a very fast evolution. After 50 days was already in the nebular phase, and the spectra shows down here. So we have that there is a complicated profile and suggests interaction. So now for many of these objects, also these ones that we have here as a SN15OS, 16AGZ, and 16AQF, we need interaction to explain or to fit the light curves, either the light curves of the spectra. And in most of the cases, for example, in 16AGZ, when we are using models, in this case, Daiichi was using some models, they found that the progenitor, this object may have a more massive progenitor. So the conclusion of this kind of analysis is that something is happening in this low luminosity host. We are having this kind of unusual evolution, and maybe metallicity is playing an important role for that. So this is just an example of some of the objects that we have, objects that go to the peak after 150 days, objects that are going down with some wiggles in the light curves, or objects that are just going down very fast and has these weird profiles. So just to summarize, II Supernovae in the optical, they show a continuum in the observed properties that suggests that they may come from the same progenitor population. II Supernovae exploding in low luminosity host galaxy, they display weaker lines, absorption lines, compared with these objects that explode in high luminosity host. And this may suggest that they can be used as metallicity proofs. So this is one thing that we need to explore. We didn't find a correlation between the plateau duration or the hydrogen envelope and the expansion velocities or the explosion energy with metallicity. These two things suggest that maybe the mass loss for red supergiant is independent of metallicity. And this point is important, and I think many models now are showing the same results. So in red supergiants, mass loss is independent of metallicity. We have that II in low luminosity host. They may have more massive progenitors, so we just have for now maybe 1-2 cases, but we need to explore this with more data. And if that is the case, we may solve the red supergiant problem, so we need to explore this also. And for sure, the peculiar supernovae are found in this low luminosity host. We need different explosion mechanism, or the progenitor maybe has some properties that are related with the metallicity that produce these weird objects. And that's it. Thank you very much.
Thank you so much, Claudia, for this interesting talk. So just remember to everybody that if you have any question, please raise your hand or write that in the chat. But warming up the situation, I just want to make you a general question that we used to do in this kind of seminar. Have you had any female scientific role models along your career that maybe that inspiring you, or?
Well, not really. And that's very sad, because I remember when I was in high school, all teachers were men for chemistry and physics. And when I went to the university for my bachelor, actually I wanted to be teacher, because for me, all people working in science, the only thing that we're doing was teaching. So I really wanted to do that. And in the university, I didn't find many women neither. And just when I was finishing the bachelor, I realized that was like I can do research, that I can do science. And so I went to Chile for my PhD, as you mentioned at the beginning. And in Chile, the things are a bit better, but still we have problems finding role models for women. So I think this kind of thoughts and all outreach that we can do as a woman to motivate girls to continue in science is very important. Because if you don't know, so you don't want to do the things that you don't know they exist. If you see there are many women in science and science school and you are like good for that, you will try to do it. So yes, we need to continue with this. We need to motivate our girls.
Yeah, completely agree. So I don't see any hands yet. So I have a curiosity or a question. So you, so if I understand correctly, so you mean that mostly all peculiar supernovae, Corcola supernovae, came from low luminosity host?
At least Titus.
But
yes.
In that moment, I have not in my mind any other example, but it seems to me weird that it's always happened in the low luminosity host.
Yeah.
But they are all different, so they have different. So probably the progenitors have different properties because they don't follow. When you say peculiar, is something that this is outside of normal behavior of supernovae, but not all of them have the same behavior. So
yes, yes,
I don't know.
I agree. So when I say peculiar, it's because they are not following the standard things, right? But if we analyze the likers of them, of the peculiar ones, they are also different between each other.
Yeah.
So yes, but we for sure we need to explore more in detail that. The good thing is now with this with the surveys that that are scanning the sky every day, so we are finding these objects in this low luminosity host, and the sample is increasing very, very fast. So
yeah, but
for
also
sure we will
some of the objects that you saw at the end were most peculiar because of interaction.
Yes, and that's one thing that we didn't think. I don't know, like 5-10 years ago, that interaction was that's important, because always when people talk about interaction, it's because you see the features of interaction in the spectra, but apparently now, well, that's not, maybe it's not the case. And we need to really understand what is happening with interaction.
Or maybe this is also some quick explanation. Whatever you see different, you say, this is interaction.
Yeah, because it's the easiest.
But maybe it's not exactly the right answer. Yeah. So I see Marco that has the hand up. So Marco, if I unmute you.
Oh, yes.
Yeah, hi,
Can
Marco.
you hear me?
Yeah.
Yes.
Okay. Thank you, Claudia, for this very nice review. I have a comment on the red supergiant problem. In a series of recent papers, we demonstrated that the red supergiant problem actually is not a problem at all, in the sense that it can be naturally explained with our latest set of models. And the explanation is very simple, in the sense that, at least this is what we found, that starts with masses larger than 20 solar masses and lower than 40 solar masses. Actually, they become red supergiants after the core hydrogen depletion, stay on the red supergiant stage for a while, and then, because of the mass loss due to the formation of dust, they turn to the blue and explode as type 1b supernovae. So this is the reason why we do not predict and do not expect stars with masses higher than, say, 18 solar masses to explode with an extended hydrogen envelope. So you didn't address at all, these papers. So this is why you don't believe to them, or is because it's another reason for that?
No. I didn't talk about that because that involves 1BC. And well, I'm pretty sure that many of these objects are going to end the lives at 1BC, but I don't know many works about it. So I know there is Young in 2009, there is your work, but it's it's true. There is a missing population, and for example, in the work that from Laureano Martinez, all analysis that were shown there was just for II Supernovae. So was one suggestion that we have was that maybe do the same analysis using the 1BC sample that is from the CSP, that is a very nice sample, to see what is happening there and to see if maybe these progenitors are the progenitors of 1BC. But yes,
okay, but except for the 1BC, the main point is that we do not predict stars with masses larger than 18 solar masses to explode as a type II supernova.
Yes.
So this is perfectly consistent with the lack of red supergiant progenitors with masses larger than 18 solar masses.
Yes.
And this can be explained simply because of the effect of mass loss during the red supergiant stage.
Yes, but also that creates some problem maybe, because if that is the case, so what happened with the binarity for 1BC?
Okay.
So there's, I don't know. So can I ask you that? What happened with binarity?
I don't know. It's difficult to
Who knows? Who knows right now?
So yes, so I know your work and I know the other works about it, but as I don't really understand what happened with binary, so I prefer them to talk about it. But it's not that I don't take that into account. I know there is there, but yes, I like to explore more that part because it's quite complicated.
Yeah, but for the same reason, maybe when you say that with this peculiar object, you resolve the problem of the red supergiant problem, maybe it's not exactly because your object is not exactly a type 2P. I mean, maybe it's another object. I mean, it's not that you resolve the problem of the red supergiant because you find this magnitude. Maybe this magnitude, this value of the mass, maybe this is because the binarity or maybe another reason.
Yes. But well, when we said we solve the problem is that we find maybe massive progenitors for hydrogen rich. That is the thing I want to say. Yeah.
There are cases of type 2Ls in which you have more massive progenitors, but maybe they are binaries. Yeah.
Yes, they are included. Yeah.
Okay, thank you, Marco. I think Andrea have another. Yeah, it's unmute. Yeah.
Thank you. Okay, as usual, great talk, Claudia.
Thank you, Andrea.
I have a comment on your what you said before on the continuous properties between type 2P and type 2L supernova that might suggest that there is a continuing progenitors properties. Honestly, I would be a bit more cautious about this because you said that you type 2 supernova arise from red single stars, red supergiants in a relatively small range of masses, as also mentioned before. Type 2 supernova are much more complicated. You know, here they are much more debated. They may have a much broader range of masses. We don't know the role of the binarity, the metallicity, and so on. So I find honestly I would be honestly a bit more cautious in claiming continue also in the progenitor properties between type 2L and type 2P.
Okay.
It was a general comment.
This part, yeah.
I have another
comment. Yeah, because for sure, well, I understand your point, but for example, here when we said that there is a continuum, is based on these objects, but we have, for example, Supernovae 98S or 16 GSD, that they are very linear, but they are far from this. they are not in the continuum, and I think it's because of interaction for that cases. But yes, you are
it's,
right.
it's the comment of
Yeah,
the progenitor population that
yes,
find a bit
okay. Thank
danger.
you.
Another comment is on the on your finding on the 1987-alike population in low metallicity galaxies. There is another study of Tadia et al. Well, they don't disagree about this, honestly, but they found that it was a bit more, a bit less clear the correlation between this type of type II supernova and the low metallicity environment. For instance, you didn't reported here an object that was a 1998A that was photometrically very similar to other objects of this class, but it belonged to a bright metal-rich galaxy. So I don't honestly find this strong correlation, let's say, between this kind of properties of the supernova and the fact that they belong to low metallicity environments. There is another point here to remember. The evolution of 1987A was somewhat driven by the post-merger evolution. So it was the result of a merger. And I don't honestly see a big correlation between this kind of evolution and the fact that the host galaxy was a metal pool.
Okay. Yeah, well, I know there are like 3 87A that they are not in these metal poor galaxies. I think it's 2006 AU, the object that you mentioned, and I think it's 2000 CV or something like that. Yes, but most of them, that's the thing, they preferentially explore in this low luminosity host, and maybe they have different paths. So yeah, yes, the problem is there are very few, and we also need to explore this kind.
Yeah, but the fact that they come from, they're the result of a relatively recent merger. This is not strictly correlated with the metallicity of the environment. This kind of evolutionary path, in my opinion.
Okay.
Yeah, that comes to the same question that I made you before. So the fact, I don't think they are strictly correlated to low luminosity host galaxies, I think. But you are the expert in the statistical field. And
yeah, but well, but the metallicity is low, or at least for 2 of them is solar. So most of them are low metallicity. That's
okay, I have, thank you, Andrea. I have another question from Giorgio. Giorgio, do you want to make the question by yourself? I can unmute you if you are, yeah, you are unmuted, Giorgio.
Okay, hello, Claudia. Thank you for the very nice talk. And yes, as I wrote in chat, I just have a very quick curiosity. When you show the cumulative distribution of the progenitor masses for supernovae type 2P that were obtained through hydrodynamical modeling, if I remember correctly. So my curiosity was, are they all obtained through the same model, or at least models that use the same assumptions? And if not, is there an influence on the estimated mass?
So the models were, they are different, so different configurations, so different masses and different
yes,
energies.
No, of course, yes. No, I mean,
but it's the same assumption that the mass loss is some number, and yes. So actually, for this sample, they were like 5 objects that they didn't fit with the standard models, and then Laureano has to increase the mass loss.
Okay.
So to fit them, but for this one is using the standard assumption that the mass loss is a particular number that they explore in a particular way. But yeah.
And I see a couple of them have very high errors. That I guess depends on, I don't know, very high uncertainties on the nickel estimate or something like that. Thank you.
One thing with these models, for example, is at the beginning, in the first 30 days, they didn't pay attention too much to the fit because the models don't include CSN interaction, and the CSN interaction is very strong, or that's the idea, at the first 30 days. So that's why they don't pay attention to that, and they just go to like the plateau and the tail. But yes, that the sonar center is in the estimations they have.
I see. Thank you.
Thank you.
Okay, thank you, Giorgio. Thank you, Claudia, again, and thank you all the question. But I think it's time to close today's seminar. Thank you for your attention, and just remember that next month we have another interesting talk, because this is the celebration of the woman in science, so this is a special talk. So I hope to see you all again next month. So thank you very much and have a nice afternoon. Bye.
Thank you very much.